Back, everybody. So our first speaker this afternoon is David Zureick-Brown from Emory University, and he'll speak on progress on Mazur's program B.
Great. Thank you for the introduction and invitation to speak. Also, thank you for coming to the number theory talk that has air conditioning. Also, the slides for this talk are available at my website. Either add slides to the end of the URL or there's a link there. I'll start by setting some notation. So I'll look at fields, K, usually number fields, but fields K of characteristic 0, the absolute Galois group of automorphisms of K bar over K. This is a profinite group with a topology. And if you have an elliptic curve over K, then the end torsion over K bar is Z mod NZ squared, but not over K. So this gives rise to a package of representations. For each n, you get the mod n Galois representation. The Galois group, the automorphisms, act on the coordinates, say, of the torsion points over Q bar or K bar. As n divides m, or if n divides m, these representations are compatible. So you can take their inverse limit along powers of L to get the L-adic, or even the best of these we call the adelic rho sub e, which is just the big inverse limit of all of them. So this one object somehow contains all of the information of all of the torsion of the elliptic curve for each n. And this talk will be about images of these representations. And the easiest way to start is to look at the image of the adelic one. So GL2Z hat is a profinite group. It's uncountable. And Serre proved in '72 that if you have an elliptic curve without CM, then the image is open. Now, open means finite index here. GL2Z hat is compact. And you can interpret this in a couple of ways. One is to say that, well, GL2 decomposes as a product of GL2ZPs. And for a subgroup to be open, this would tell you that for fixed E without CM, for all but finitely many P, the p-adic representation is surjective, and maybe there are a few small p for which it's not. Conjecturally, this is bounded in the sense that, I'll talk more about this, kind of the point of the talk. Conjecturally, for p greater than 37, this image is surjective for non-CM. Another way to think about this, going back, is we're looking at GL2Z hat is the inverse limit of GL2Z mod NZ, saying that the image of rho E is open is equivalent to the images of the mod n representations as you vary over n to eventually become bounded independently of n. Another useful way to think about this is the following. So let's stick to the mod n representations, and we'll stick to k equals q for now. So I can take the image of GQ inside of GL2. There are lots of extremes. This could be trivial. This could be the full group GL2. This image has the following alternative Galois theoretic interpretation. Join to Q the coordinates of the n torsion points of E, and this gives you some interesting finite field extension. Equivalently, this is the fixed field of the kernel of the representation above, and the image H of n of this representation is equal to, by an exercise, the Galois group of this concrete extension you get by joining the torsion points. So if you don't like Galois representations, this is a very concrete object. Just to join the coordinates of torsion points to Q, look at the Galois group of that field extension, and let's study it. So Mazur's program B, I'll explain how this generalizes his other work, is to classify all possibilities for H of n. And I'll have to talk about what classify means. So where does the term program B come from? Here's a snippet from his article in the rational points, his article, Rational Points on Modular Curves, which is a survey article in one of the modular functions of one variable volumes. He says, Theorem 1 also fits into a general program. Okay, here it is, classify possibilities for the adelic image. So I finally, a few months ago in Hawaii, got to give this talk to Mazur at the Mazur session, the AMS meeting, and I got to ask Mazur, so this is program B, what's program A? So audience participation, what's program A? There is no program A. So there's a theorem 1, or theorem A, program B, and conjecture C. Problem 1, program B, and conjecture C. So problem 1 is about boundedness of torsion over number fields, and conjecture C is about boundedness of isogenies over number fields. So what does this have to do with Mazur's other theorems? Let's do a few examples. If you have an elliptic curve with a k-rational torsion point P of exact order n, this forms part of a basis. Let Q be a complementary point. So P and Q form a basis. Now, because P is defined over K, it's fixed by gal of K bar over K. So on the other hand, the point Q we know nothing about. When you act on it by Galois, P and Q is a basis, so it's multiple of P plus multiple of Q. However, with the choice of basis PQ, the element sigma acts via the matrix 1 star 0 star. Side note, it looks like I took the transpose of this matrix. This is true. The literature is slightly inconsistent about whether people are acting on the left or on the right. This doesn't cause errors in more or less any of the existing literature other than my own paper, because, for instance, the Borel subgroup is conjugate to its transpose. So for many of the maximal subgroups, which are the most studied, the transpose of a maximal subgroup is transpose, and they're conjugate in that case. On the other hand, it does matter for general H. Similarly, if you have a cyclic rational isogeny, and if P is a generator of the cyclic kernel of phi, and if Q is, again, a complementary point, P is no longer fixed, but the subgroup generated by P is fixed. So when Galois acts on P, it sends it to some multiple of P rather than multiple of P plus multiple of Q. And then again, it acts on Q however it acts. So the matrix of sigma with respect to that basis is in a Borel, star, star, 0, star. If you pick a different basis, you get a subgroup conjugate to a Borel. And for most of these talks, any inclusions I write will be up to conjugacy rather than on the nose. So to recap, the mod n image of Galois is conjugate to a subgroup of a Borel if and only if K has a k-rational cyclic isogeny. So you can rephrase questions about existence of isogenies in terms of Galois theory, in terms of possibilities for the image of Galois. So the Borel is an example of a maximal subgroup, and there are other maximal subgroups. These are somehow the most important of the subgroups, because if you would like to prove that the image of Galois is the full group GL2, well, if you can show that it's not contained in any maximal subgroup, then it's equal to GL2. A next example, so the left, star 0, 0, star, that's a split carton. Those are the matrices which, with this basis, expand each axis. And then, of course, 0, 1, minus 1, 0 normalizes this, because if I switch the axes, expand them, and then switch them back, that is an example of expanding the axes. There's a moduli interpretation of this as well. It needs a few lines. So the mod n image is contained in the normalizer of a split carton, but not the carton itself, if and only if, okay, I'll say it, there's an unordered pair of cyclic isogenies. They're not defined over K, but they're defined over some quadratic extension, and they're Galois conjugate, and their kernels intersect trivially. That's still a useful moduli interpretation. I was surprised to learn last summer from a talk by Robledo that the non-split carton, one of the other maximal subgroups, also has a useful moduli interpretation, well, other than the kind of tautological one. And that, yeah, it turns out to be useful. So next, how do you attack such problems? So modular curves, the modular curve xn of k, I define to be, and I really mean this version, the geometrically disconnected one, the moduli space whose k points are cusps and, or an elliptic curve together with a particular choice of basis of the intorsion. As I've set it up, because of the Vous pairing, this is not going to have any k points, except in the case when n is 2. It's a stack, but not a scheme in that case. But this moduli problem still exists. If the basis p comma q, if each p and q are defined over k, well, then the matrix of Galois acting on them, it fixes p and q, so the image of Galois is trivial. So if the basis of your torsion is rational, the image of Galois is trivial. There's some additional level structure in general that I'll admit. So this is this version of the moduli problem has q components which are connected but not geometrically connected. For general H, if you have a subgroup, I'll say the level of a subgroup H is the minimal n such that H contains gamma of n, the matrices reducing to the identity mod n. H acts on the modular curve x of n, essentially by change of basis, and I'll define x lower h to be the quotient x of n mod h. Points of this roughly correspond to cusps and elliptic curves whose image of Galois is contained in that subgroup H. This is something you can work out from the definition as this quotient xn mod h. There's an additional bit of level structure, which I'll admit for this talk. Additionally, there's a little bit of stackiness that matters that I will mostly admit as well. For instance, minus the identity acts trivially. Even if minus the identity is not in the subgroup H, there is still some funniness that can happen at the cusps, or at the CM points. And Mazur's program B is, I wrote Q there. I'll say this in a funny way, compute every rational point on every symmetric power of every modular curve. So for today, compute every rational point on every modular curve. What does this mean? Well, sometimes the genus of x sub h is 0. It could be a pointless conic, or it could be P1. And I'll say a bit more about what it means to compute x sub h when it is isomorphic to P1. But essentially, I want to know explicitly the isomorphism between xh sub h in terms of moduli and P1. Or at least, I would like to know an equation for the map to the J-line. That's usually good enough. It could also be an elliptic curve of rank 0 or positive. In general, these will be higher genus curves, which by Falting's theorem, the Mordell conjecture, have finitely many rational points. However, some of these have sporadic points. For instance, x naught of 15 is a rank 0 elliptic curve, but it does have some points that are not cusps or CM. There is a rational cyclic degree 15 isogeny. So we can argue a bit about what sporadic should mean, but for the purposes here, it means a point which is not a cusp or CM point on a curve, that modular curve x sub h, that has only finitely many points. And these do happen. You can compute the genus of x sub h group theoretically, essentially via Riemann-Hurwitz. And more recently, you can compute the number of FQ points for any power of a prime of good reduction, so not dividing the level, via moduli and enumeration. So David Zwina and Drew Sutherland did this in the case when x sub h was an elliptic curve. Drew realized that this had some utility in the higher genus case. It's a bit tricky to correctly handle the fact that these are naturally stacks rather than schemes, and the fact that for a general subgroup H, it's not completely clear what the level structure is unless you actually work out what happens when you take this quotient. On the other hand, this is useful. There are some cases where you can compute that there are, say, no F2 points on this modular curve, and hence no rational points. Or, this was useful for us, if you can compute the Fp to the n points for enough values of n, you can compute the zeta function of x sub h, and hence how its Jacobian decomposes mod prime. There are lots of computational tricks that I now have access to because of Drew's code. The genus, and in fact the gonality, although that second fact is more difficult, of these go to infinity as the index of the group H approaches infinity. This isn't quite the same as saying there's infinitely many, say, rational modular curves because you can often take twists of them, but at least up to twisting. This is not really a problem. So what do these subgroups look like? Historically, in things like Mazur's theorem, you look at modular curves where the level is prime, but I'm really explicitly in this talk interested in the cases where it's composite or better powers of primes. So here's a sample subgroup due to Serre. I'll let h of integer mean the reduction mod that integer. And here's a subgroup, which is, let's build it from the bottom. Mod 2, it's the full subgroup. Mod 4, it's missing just a little bit. Mod 4, it's everything. And let me explain what I mean. So the mod 4 image is, I can do this. The mod 4 image is contained in the pre-image of the mod 2 image. I hope that's clear. Of course, the kernel of reduction of phi1, these are the matrices which reduce to the identity mod 2. These have a nice structure. If you multiply two matrices of the form I plus twice a matrix, well, it's like a Lie algebra. You add the matrices because 4 is 0, mod 4. So actually, these kernels have some structure as a Lie algebra. You can get some mileage out of that. But for us, I just care that these are, well, in this example, F2 vector spaces. And if I'm thinking about a group in this way, where I'm working mod some powers of some fixed prime, the most sensible way for me to think about these groups is not by writing down matrices that generate them, or even moduli most of the time. Rather, I usually want to know, I understand GL2 of a prime pretty well. I want to know what the reduction mod L is, and then how these reductions stack on top of each other. And even then, I want to know the discrepancy between the group H4, for instance, being equal to the pre-image of the group mod 2. And the dimension of this kernel, in some sense, measures that discrepancy. If it's 4, like in this case, H4 is equal to the pre-image of H2. But in this example, the mod 8 group is not equal to the pre-image. It's index 2, and it's missing just a little bit of the kernel. I can tell you this group explicitly. I mean, here it is. Pick a subgroup of F2 cubed, and then pull it back via the determinant and sign map. A typical subgroup looks worse. It was not useful for me to think about the moduli interpretation of this group that appeared in our project. This was a group that was surjective mod 2, index 2 mod 4, index 8 mod 8. So it gets worse before it gets better. It gets a little better. Mod 16, it's only missing a little bit of the kernel. And then mod 32, it has the full kernel. Once you're working with the power of a prime larger than 8 or 9, there are exponentiation maps. And the dimensions of these kernels are monotonically increasing. So once the dimension of one of these kernels, past the point of 8 or 9, or L squared, is 4, it's 4 all the way up. That's why I gave it the green light. So here, this subgroup, after level 32, is just the pre-image all the way up. Yeah.
But I'm trying to understand, is this particular subgroup special in some way, or are you just sort of like...
No, I'm saying this is not special in any way. It's just a subgroup that came up in our problem. Every as we'll see in the diagram later, every other subgroup that contained this corresponded to a modular curve with infinitely many rational points. And to classify images, we had to look at this group, look at the corresponding modular curve, and determine its rational points. And so this one, I believe, had no sporadic points on it. But on the other hand, I don't think you would learn anything else if I told you what matrices, mod 32, generate this. Rather, this is just what these groups...
The group, right? There's more than, is that
What's
right?
that?
These numbers don't specify.
And these numbers don't specify the group. I thought you would ask this. I was thinking about this last night. For instance, if the group mod 2 is trivial, there are plenty of subgroups of I plus twice M2, which have the same order. So that doesn't specify it, even up to conjugacy. But nonetheless, I think once I know these numbers, there's not much more that I mean, I can ask if it's contained in a Borel or something like that, but there's not much more that I want to know after this. So this is a typical subgroup. These exist. You have to consider them to classify images. Let's do a non-prime power level case. there is a surjection from GL2 Z mod 3Z to GL2 Z mod 2Z. If somebody who understands representation theory over F2 better than me has a great description of this two-dimensional representation, let me know. I actually don't care what the map is. The easiest way to describe it is GL2 Z mod 3Z has order 48, so the 2-celo subgroup has order 16. That's index 3. It's not normal. You can check that there are 3 2-celo subgroups, so GL2 Z mod 3Z acts on the 3 2-celo subgroups. You can check that that actually gives you a surjective map. Rather, GL2 Z mod 6 decomposes as a product of, by the Chinese remainder theorem, GL2 Z mod 2 and Z mod 3. So I can take the graph of this morphism, but viewed as a subgroup of the product. Almost by definition, this graph will surject under each composition to GL2 or G mod 3. But it's a graph. It has order equal to 48, the domain of the morphism you're taking the graph of. So it's not equal to the full subgroup GL2. I learned about this example from Nathan Jones. He and Julio Brau have a paper where they check, although these days this part's mechanical, you can check that the corresponding modular curve has genus 0 and a rational point. So they actually work out an equation for the J-map. This particular group has a nice moduli interpretation. If the mod 6 image is contained in this group, then the 2 torsion field, the field you get by adjoining the coordinates of the 2 torsion points, is contained properly in the 3 torsion field. And there are a finite list of subgroups that have this property if you want to get an if and only if statement. What does it mean to compute the rational points on this modular curve? Well, they also give the map to the J line. These are both P1s. And so in this case, they can phrase their theorem as an elliptic curve has image contained in this group if and only if its J invariant is of the form 2 to the 10 3 cubed times t cubed 1 minus 4t cubed for some element t of your field k. Of course, there is always going to be some field extension over which your torsion points are defined, and over that field extension k, the mod 6 image will be contained in this group because it's trivial. And correspondingly here, there is going to be, for whatever j of e is, some t solving that equation over some number field. So this is fairly explicit. And this is what it means to compute the rational points when the curve is rational. So classification of images, I'll go more quickly through this part. Mazur's theorem classified possibilities for torsion on elliptic curves. Correspondingly, this translates to a classification of when the image of Galois can be contained in 1 star 0 star. He also studied the Borel corresponding to isogenes. And the first time I got scooped as a graduate student, I was thinking about the case of normalizers of non-split cartons. And Boulou, Perrant, and Reboletto, there's an analyst paper where they, or a couple of papers where they work out the case of normalizers of non-split cartons. One of the more exciting developments for me recently is their theorem did not work for L equal to 13. In that case, the corresponding modular curve was a genus 3 curve with rank 3 Jacobian. And the non-abelian Chabuti collaborators very recently have, I think it's like a 47-page paper handling just that modular curve using new techniques. So we can change that to greater than or equal to 13. So the main conjecture, I stated Serre's theorem, which says that the image is open, but Serre's theorem is non-effective in the sense that if you hand Serre circa 1972 an elliptic curve, he can tell you a bound on, he can tell you that for large P, large L, depending on P, on E, the mod L image is surjective. That group H sub L is equal to GL2, but that dependency could be on E. We actually still don't know that. We're close, but also kind of far away. So conjecturally, for large L, greater than 37, and a non-same elliptic curve, these images are easy to understand. In the remaining case, I've tried nothing and I'm all out of ideas. So let's ask a maybe easier problem. So if you know this horizontal image conjecture, then it follows kind of from pure thought, thinking about these modular curves and their genera, that, plus some group theory, that actually once you have a bound, an explicit bound, 37 say, on L for which HL is surjective, you actually get a full bound for the index. So this follows from the L greater than 37 conjecture, and a problem I've thought a lot about is, well, assume this conjecture and then try to compute that in. So again, find every rational point on every modular curve. So my first theorem about this with Jeremy Rouse, we handle the two-adic case. So of the full adelic image, we prove, I wanted to phrase it in a way that fits on a line. So we prove that for a non-CM elliptic curve, the index of the two-adic representation divides either 64 or 96. And all such indices dividing one of those occur. Although 64 only occurs twice, I'll show you those. That slide of the scary group from before, I stopped at 32. So we don't have a conceptual reason other than thinking about rational points on modular curves why 32 should be enough. But once you know the mod 32 image, you know everything. There are 1,208 different subgroups which can occur for non-CM elliptic curves, explicitly as the image of some elliptic curve over Q. But there are only 8 of these subgroups which occur finitely often. So 1,200 of these groups occur infinitely often, either as P1s or positive rank elliptic curves. So here they are. Here's a graph of them. This is the first piece of mathematics that I printed out and framed and put on my office wall. The nodes of this graph, this is made with the program Graph Viz.
Did you check them off on your office wall as you did the curves?
Absolutely not. For the other primes, I did. I did that after we finished the paper. And actually, this isn't even all of them. These are the subgroups which contain minus the identity. If a subgroup does not contain minus the identity, it is an index 2 subgroup in a group that does. Just take the group generated by H and minus the identity. These are ordered by inclusion. It's a directed graph. You can tell that there are little boxes that are colored. The boxes have labels. The colors correspond to genus, but you can't read it on, even with the giant screen, you can't read it here. And the way this is organized is the very top group is GL2 of Z2. And then the 4 groups below, those are subgroups of GL2 Z2. And then the next level is maximal subgroups of the maximal subgroups, and then maximal subgroups of the maximal subgroups of the maximal subgroups, and so on. And the red dots, you can still see that are boxes. Those are genus 0 with a point. And so you get just a bunch of modular curves with infinitely many points. But of course, we know that as the index increases, eventually we get non-rational and then eventually non-elliptic, so higher genus curves. So you can see near the bottom, you have blue. I think those are genus 3 or 5. There's some genus 7. There's a bunch of genus 2, and a bunch of pointless conics and elliptic curves. Let's talk a little more. So data. William Stein taught me that you should try to prove true theorems. So the first thing we did when we were working on this was open up the Cremona database that only had a mere 1 million elliptic curves at the time, and just take data. And so a couple of comments. We have no idea why the first few lines have 72, 72, 17, 17, 57, 57. We don't have an explanation for that. The obvious ones about comparing indices or degrees don't quite work. 64, we found 0. These are all the divisors of 64 or 96. There's a bunch of CM. But there actually are exactly 2 elliptic curves whose index, two-adic index is 64. The reason we didn't find them in the Cremona database is I had to factor their J invariants to fit them on one slide. These are rational points on X non-split of 16. Hegner, this is a hyperelliptic curve of genus 2. I could have just said genus 2. Hegner worked out equations for this. And Bucher-Baran, using elliptic Chaboutier, worked out what the rational points on this were. Hegner actually made a mistake in his original paper, just a transcription error from one line to another. He lost an exponent in one of the terms of the equation for his J invariant map. So there's actually an error in Baran's paper that we traced back to, I mean, we thought we made a mistake, an error in her paper based on a typo in Hegner's paper. Hegner. Yeah. I have some applications. I think I'll skip some of these, but I will talk about Jeremy's original application for this. So he has an application to arithmetic dynamics. Pick a point of infinite order on E and ask how often the order of its reduction is odd, often in terms of Dirichlet density. And he and Rafe Jones worked out that the answer depends on some integral in the Haar measure sense over the two-adic image of Galois, and a little bit of Kummer theory. And so Jeremy, part of his motivation for this project, which he didn't communicate to me until after the paper got rejected the first time and the referees asked for more motivation, was, it's the only negative thing I'll ever have to say about Jeremy, he's great, was this application. So what we show is that for a generic elliptic curve over Q, so in particular one whose two-adic image is the full group GL2Z2, you actually have a slight bias, a little bit over half of the primes, P has odd order modulo, a little bit more than half of the primes, but the extremes, over Q at least, are 121 over 168 and 1 over 28. So now that application's in the paper. We actually work out the integrals that tell us the answer. And for now, I'll skip the other applications. A couple recent theorems, though. So David Zwina's name will appear quite often. Working mod L and assuming some conjectures. And I'll show you on a more restrained graph in a minute what this means. So for instance, the L greater than 37 conjecture, but he was also assuming, for instance, that there were no unknown rational points on the cursed curve of level 13, which is now not a conjecture. Classifies what just the different mod L images are. And so part of this is you need to enumerate what the subgroups of GL2Z mod LZ are, understand the corresponding modular curves, maybe do some type of Chaboutier on them. He also worked out an upper bound on the index of the adelic image. There's a little bit of a really wonderful cheat here, which he doesn't work out what the possibilities for the group are. So for instance, if there are two groups which have index 220, and he can show that one of these groups occurs as the image of Galois, he forgets about all of the other groups with that index. So he works out what numbers can occur as the index, but doesn't handle all of the groups. And I phrased it in a way to fit on one slide. Also recently, Sutherland and Zwina, in all of the prime power level cases where the corresponding modular curve has infinitely many points, they work out, well, in the genus 0 case, the map to the J line with proof, and in the genus, exhaustively everything with proof. And in the genus 1 cases, they work out when the rank is positive and models in this case. I'll skip entanglement. My current PhD student, Jackson Morrow, worked out if you have a composite integer, which is a power of 2 times a prime, he worked out, not completely, there were a couple of tricky cases, but almost exhaustively what the possibilities for the image of Galois are. That's a fair amount of work. And then an ongoing project with Jackson, Jack, and a few who aren't here are trying to handle, well, we're not going to be able, I say partially, there are some genus 2000 modular curves which arise that we don't know how to handle. And there's a bunch of high genus curves. But we're at least writing a paper where we say, here's what any sane person can say about this problem, and then here are the remaining cases. Maybe in 10 years we'll have better computers. And I'll skip that application. Insane people can. I mean, we were insane to consider the two-adic case. Here's a proof template. So the easiest part is to compute the graph from before. So we'll just say arithmetically minimal means there's some group theoretic conditions. You want the determinant to be surjective, or else considering the Bay pairing, the image will never occur. There's actually a group theoretic condition for an elliptic curve to have, sorry, there's a group theoretic condition for x sub h to have a real point that we include there. And then by minimal, we just mean, so whatever subgroup corresponds to that dot, we don't have to consider any subgroup properly contained. Once we find all of the rational points on that modular curve, there's finitely many. And so any modular curve that maps to it also has finitely many. So there's somehow a finiteness to this problem. So the minimal ones are the kind of bottom colored nodes that we have to consider. That part's actually fairly easy. We have difficult lives. Jeremy and I worked that out on Magma on a bus in Hawaii while taking a 6-hour tour, and then produced that graph. The next part is to compute I mean, in principle, you can use Mazur's method or similar techniques for some of these x sub h's, but even in Mazur's proof, for instance, Kinku, I'll show this on a later slide, worked out for x naught, well, x naught of 13 is a genus 0 curve. X naught of 13 squared is a genus 8 curve. And if you want to understand isogenies over Q, you need to understand points on that curve. It's the power of a prime, and Mazur's method, as that existed then, didn't work for that curve. So Kinku worked out equations for this genus 8 curve and showed that it mapped to a smaller genus curve and determined its rational points. So our approach is compute equations for each node on that graph. If it's a P1, we compute whether it has a point or not and the J-map. And then find with proof, using a combination of methods, we end up using maybe 12 or 13 different techniques, all of the rational points on each x sub h. So here's our graph in the two-adic case of the arithmetically interesting or minimal subgroups, a kind of cofinal system. Let me say a bit about the baby version of how to compute, the part I understood at the time, equations for modular curves. If you have a non-hyperelliptic curve, modular or not, the canonical map is an embedding. It's actually fairly explicit. With magma, it's mechanical. You can push a button, and it will compute the equations for the canonical map with respect to some basis, et cetera. This map is an embedding for something non-hyperelliptic. In Petri's theorem from the 20s, Petri was a student of Grobner, he kind of worked out part of what a Grobner basis meant in his thesis to prove that for a general curve, general here means not trigonal, not a plane quintic, the relations, rather, the equations defining the image of C are all quadratic. And by Riemann-Roch, you can calculate how many of them there are. Now, for a modular curve, well, a modular form is a differential on the modular curve. So you can do the calculation of what the relations here are using power series expansions at the cusps, meaning the corresponding modular forms. So you have a way to, and we know a lot about how to compute expansions of modular forms. So the summary of this is, here's an example. You can compute fairly quickly. This example took me an hour or two by hand or with magma. So x1 of 17 is a non-trigonal genus 5 curve. It canonically embeds into P4. It's a complete intersection, so there should be 5 quadratics vanishing on a general genus 5 curve in P4. These Q series are, up to some precision, just the power series expansions of these 5 cusp forms at infinity. And we know a priori that these cusp forms satisfy some quadratic relations. Sorry, I said 5. I meant 3 quadratic equations to curve in P4. So you just assign, how do you do this in magma? You just assign a variable to each form, and then you assign kind of free variables for the coefficients of the quadratic equations, and then you keep increasing the precision on the modular forms and plug them into these equations until you determine what the coefficients are. And you know that this has to stop at some point. So if you know how to use magma, you could do this example in a couple of hours. If you're, the hardest part is the linear algebra of, like for the cusp forms, you just type in cusp form and it gives it to you. So this is what I understood maybe 15 years ago. This is not quite what we do, but it's related. So Jeremy had a nice idea. If you have an index 2 subgroup of groups, then the corresponding map of modular curves has degree 2. And so the corresponding extension of function fields is quadratic. So if we have a set of equations for x sub h for the larger group, we only need one new equation, and we know that it's quadratic for the curve that covers it. So we, in this in this directed graph from before, we compute everything inductively. And then Jeremy had this neat idea, which is, well, still, maybe it's really difficult, especially 6 years ago, to compute the modular forms on some weird-looking group mod 32, but you have a lot of additional information. His idea was if x sub h prime, so this is a degree 2 map. When you look at the cusps, say the rational cusps, either the map is ramified over a cusp or it splits into 2 cusps. And his idea there was, well, you can write down, if you have a cusp that splits into 2, you can just write down directly an Eisenstein series which vanishes at one cusp, but not the other. And then that can't possibly correspond to something coming from the smaller curve. And then Eisenstein series, you just have formulas to write them down directly and can compute relations. That fits on one slide. The first version of the code we wrote took like a week to compute one example. Jeremy rewrote it 7 times, and now it takes a few seconds. And I'm not sure what speeds it up so much. Other numerology. So at least for powers of 2, I said there were 1,208 groups, but these are just the groups that do not include the pointless conics. We don't need to consider them, and which contain minus the identity. So we get lots of P1s, 175 of them. We get a good number of rank 1 elliptic curves. In the genus 2 case, there are lots of cases where Chaboutier applies. The rank is less than Jacobian. There's actually 7 cases where the rank is equal to 2. Chaboutier's method doesn't work there. And we use a big combination of different techniques, some that kind of existed, like elliptic Chaboutier, and there were some that we kind of had to invent, but it gets a bit worse. So for the genus 3 curves, there were some non-hyperelliptic rank 3, genus 3 examples. In some of those, we could find some ad hoc argument, like étale descent, but it really took a lot of work, to kind of case by case, to handle these. And then it gets worse. There are some rank 5, genus 5 curves. And then for the rank 7 curves, at the time, we couldn't actually compute smooth models. What do I mean by smooth model? This inductive way of computing, we could compute some singular model, a quadratic equation for the genus 7 curve over some genus 1 curve. But the model that gave would often be singular. And we also, even using analytic techniques, couldn't compute the ranks of these Jacobians. Nonetheless, we were able to, without knowing their ranks, invent some tricks, some technique to handle these. Say it again? Right, so Adam was asking, is there a reason why the rank is congruent to 1 mod g minus 1? So actually, most of these are of GL2 type. And so the rank is for each factor of the Jacobian, the rank is a multiple of its dimension. And so for the genus 5, the case where it's a multiple of 5, the Jacobian's simple. And in the case where it's 1, it has an elliptic factor of rank 1 and then a rank 0 factor. So yes. A couple other two-adic facts, and we'll talk about the other cases. I said before, there were 8 sporadic subgroups. There was only one genus 2 curve with sporadic points. That's the non-split case of level 16. Some of the genus 3 curves had single sporadic points, but none of the genus 1, 5, and 7 curves had sporadic points. Here are my favorite parts. There are many accidental isomorphisms. Actually, these are well known otherwise. So X non-split and X split of 13 happen to be isomorphic. But these collisions just happen all of the time. So for instance, the curves in our directed graph all have good reduction away from 2. And there just aren't that many curves with good reduction only at 2. So you would kind of expect some of them to be accidentally isomorphic. By accidental, I mean there's not some reason in terms of moduli or group theory that these are isomorphic. For instance, we have plenty of pairs, H and H prime, where the number of cusps, let alone the number of rational cusps, is different for the group H or H prime. But the curves are isomorphic. So you would not expect a good reason. And best of all, it happened exactly once that there was an H such that the genus of H was, XH was 1, and it had a rational point. So it's an elliptic curve, and it was a point on itself.
Wait, David, can you go back for a second?
Sure.
Are the sporadic subgroups explained by those accidental isomorphisms where your sporadic points are?
That's a great question. Not all of them are.
Okay, so there's really no reason you know why those points are there except that they're there.
Yeah, I mean, so sometimes we have a good reason like X naught of 37 where there's an exceptional involution. But we don't have a ton of these examples, but we have the paper with Wanlin and others. We have a bunch of accidental sporadic points. Yeah. Yeah. No, it's not. Sometimes it is. All right, so there's power of 2 again. Let's go through the other primes. Let's start at 13, because with 13, I think you can read the labels. So let's reset. GL2 of Z mod 13, there are infinitely many elliptic curves. That modular curve has genus 0. And then it's a bad color. So there are 4 maximal subgroups. There's the Borel. So gray in this picture means a P1. so with the point. X naught of 13 has genus 1. The split and non-split cartons are genus 3 curves, non-hyperelliptic. Their Jacobians have rank 3. These are now handled. There's actually one exceptional case. So if you projectivize, so you take the image inside of PGL2, you can take the subgroup S4, the symmetric group, and pull it back. That will give you some exceptional subgroup of GL2Z mod 13Z. In general, we understand the rational points on the modular curves corresponding to these, exceptional subgroups. But again, for some small primes, maybe like the original arguments due to Serre and others don't work. And this is an example of that. So actually, X sub S4 of 13 is a genus 3 curve whose Jacobian has rank 3. There are actually sporadic points on this. So this is an example that's not explained by any accidental isomorphisms. Reboletto, with this necklaces description on X non-split, was able to use that moduli interpretation to show that the Jacobians of XS4 and X non-split are isogynous, but they can also check. These are just plain quartics, so they can just check that the corresponding curves are actually not isomorphic, even though their Jacobians are isogynous. So that, to understand completely the 13-adic image, there's one more curve that I hope somebody from this side of the room can handle. Moving in the other direction, so if a group is contained in split or non-split, we don't have to consider that anymore. There's only finitely many possibilities, but then for the Borel itself has maximal subgroups. For instance, these are upper triangular matrices. One of the entries on the diagonal could be a square. That's a subgroup of the Borel. That's a maximal one. And so actually, for many of the maximal subgroups of the Borel, you also get a genus 0 modular curve with a point. And then you look at the maximal subgroups of those maximal subgroups. Maybe the top entry is, I didn't think this through, a 4th power. But then those corresponding modular curves each have genus 2. And David Zwina worked out the rational points on all of those. The shapes correspond to level. So everything except 169 in this picture is level 13. By level, again, I just mean you take the group mod 13 and you take preimages all the way up. But then again, for the Borel mod 1, so the matrices that are upper triangular mod 169 are also upper triangular mod 13. And Kinku worked out the modular curve corresponding to the box and its rational points. So next to 2 and Isl C3, this is the case we understand the best. There's not that much that can happen. But again, their paper using quadratic Chaboutier, non-abelian Chaboutier to handle the cursed curve, non-split 13, is long. It's 47 pages. It's not an exercise. 11 is both better and worse. So it's the same type of situation. GL2, OK, it's a P1. Actually, X non-split of 11 is a rank 1 elliptic curve. So you also have to look at non-split of 121. Now, X non-split of 121 has the same. Oh, I didn't mention yet why the non-splits are so bad. You can work out, like via the winding quotient, via integrals on the upper half plane. You can work out that every factor of the Jacobian of a non-split Cartan modular curve has rank at least equal to its dimension. So Chaboutier's methods don't apply. And the same is true for 121. There's an additional curve where the group isn't interesting, but it has high genus and rank equal to genus that we don't know how to handle. But then the blue filled in bubbles, these all happen to be elliptic curves, and we understand the rational points on them. For instance, X naught of 11 is an elliptic curve with rank 0. So here, the scope of the problem is not too bad, but then there are 2 cases that are just maybe impossible. So what do you think the genus of X non-split of 121 is? I forget, but the other curve has genus 511. I have these on a slide later. So for 3, I haven't stated this as a theorem yet. We're working on, again, every rational point on every modular curve. We can now handle everything that happens 3-adically except for the red bubble. The red bubble. So we have non-split mod 3, non-split mod 9. Those are both rational. And then non-split mod 27 is a genus 12 curve whose Jacobian has rank 12. Every other 3-adic modular curve we can handle. X naught of 3 is rational. X naught of 9 is on there.
Why does gnome get a curve?
This is so great. Shouldn't gnome have a curve? No, so gnome wrote a paper that's on the archive but not published. Back before you could automate a lot of this stuff, there's a subgroup of GL2Z mod 9Z, which is not equal to GL2Z mod 9Z, but surjects onto GL2Z mod 3Z. And he worked out equations for that corresponding modular curve. So it turns out to be a P1. Actually, the most difficult case on here is then working, so you see circle, square, diamond, that curve 80. This is a genus 43 curve. So last October, Jeremy and I went to visit Drew Sutherland and Martin Derricks, and one of the things we were able to handle was this genus 43 curve. Let me pause to tell you how we handled this. Well, it canonically embeds into P42, so 42 appears in a paper for us. And Jeremy actually figured out how to compute the 1,600 or so quadratics that cut out the image of this curve. And so we thought, well, what can we possibly do with this? We actually we already know for moduli reasons, these curves have bad reduction at worst only at 3. We had checked that it has mod p points for p not equal to 2, but the group is very funny looking. The group, elliptic curves whose image are contained in that group, labeled 80, have the property that their 27 torsion field is equal to the 3 torsion field adjoined zeta 27, which is as small as it can possibly be, given the constraint from the Weil pairing. And we had local reasons to expect that there were no 3-adic points on this. But this would require something probably more interesting than this project, which is generalizing Serre's results about images of decomposition groups for elliptic curves with supersingular reduction in his open image theorem paper to powers of primes. And we couldn't figure out how to do that. Instead, this gives us a model of our curve. And we thought, well, let's look at what happens if we reduce this model mod 3. And at first we were sad because it turns out the model wasn't flat. The just equations we had when we reduced mod 3 gave us a surface instead of a curve. And so we spent some time trying to find a flat model and then a regular model, so a nice model. And we went to lunch with Bjorn. And we explained it to Bjorn, and he came back to us later and said, it doesn't matter how nice the model is. If you have a Q3 point, you still have a mod 3 point and a mod 9 point and a mod 27 point. Just to see if there are any mod 3 points. The reason you want a regular model is that a Q3 point would reduce to a smooth mod 3 point. And so we checked, and there were a bunch of mod 3 points. But then we were able to show there were no mod 9 points using this model. And actually, I could double the length of the story and explain how we did that. But it wasn't by checking every mod 9 point. So anyway, actually in this picture, we found no sporadic points. I mean, so of course, the gray circles, these are P1. Oh, sorry, the gray circles, these are P1s. So these have infinitely many. So by definition, there are no sporadic points. But each of the modular curves with finitely many points only have CM and cuspidal points. So when we started this project, we were kind of happy to assume that we were never going to understand what happens to all of the non-split cartons, let alone mod powers of primes. So in our theorem that we're writing up now, we're just going to state it as with the exception of non-split carton at level 27. Well, there's always something you can try. So this curve of genus 12 over Q adjoins zeta 3, it maps to a genus 3 curve. Of course, that genus 3 curve's Jacobian has rank at least genus because it's a quotient of the previous one. But then that has a rational 3 torsion point. So there's an étale triple cover, and that has genus 7. And then all of the twists of that, except for one, map to a rank 0 elliptic curve. And that rank 0 elliptic curve has a 3 torsion point. So we can do another. There's always something you can try, and that might actually work. So I'll report back later this year. There's only 2 small primes remaining. So for 5, it's good, but also bad. Again, you can actually read the labels. The problem is there's non-split of level 5 has genus 0 and a point. So it's a P1. Non-split of level 25, I think, has genus 9 or 12 again. And then there are some other cases where the group is not interesting, but the rank is equal to genus. And then similarly for 7, there's non-split of level 49. And then there's a couple additional cases. I will say in the genus 5 case, there are sporadic points. So 2 of these curves have genus 2 and actually have sporadic points on them, but they also have rank equal to 2, no small degree atoll covers, and I'm hoping the non-abelian Chaboutier group can handle some of these cases for us. So summary of remaining work. The red are the non-split cartons of prime power level of genus, oh, I had it backwards, of genus 12, 14, 69, and 511. The greens, I'm hoping that non-abelian Chaboutier can handle. The blue is that there's actually one additional curve on there, which is genus 12, but it has its Jacobian has a 3-dimensional factor that's rank 0. And then the 2 black cases are also rank equal to genus, and we're pessimistic. So again, we have the untouchables, the non-split cartons. We have probably also untouchable, like genus 9 and 41, nothing interesting about the group, and by level I mean 7 power, 11 power. We have some that we're optimistic about that non-abelian Chaboutier can handle, and one that we just haven't had a chance to handle yet. And so somehow I'm personally happy to assume some conjectures in our final theorem for now about the prime power non-split cartons. Although, to be fair, historically, even in Mazur's method, he handled isogenies for prime level, and you had to handle prime power level isogenies on a case-by-case basis. So maybe we really do need to find the rational points on this genus 5, 11 curve. So I haven't actually talked much about how you provably find the rational points on these curves. I'll just say here are a few highlights. So of course, Chaboutier's method, elliptic Chaboutier, local methods, sieving. Even local methods, though, we sometimes had to invent some new technique because you just can't, this genus 43 curve, you can't enumerate all of the mod 9 points on that before the universe ends. And then in the original paper, there were kind of 2, if you're looking for something to talk to me about during the break, we have this argument that handles these genus 7 curves where we can kind of do a tall descent without having equations, kind of just thinking about group theory. And this technique worked a lot. And then maybe the other one I want to highlight, this is kind of weird. So if you have a curve of high genus, like 8, the best thing that can happen is, once it has local points, is that maybe it maps to a low genus curve that you can do Chaboutier on or otherwise manage. Now, on the other hand, if you have 2 fixed curves of genus at least 2, it's technically, like you know what the possibilities for the degree of a map are. You could, in principle, keep looking until you find it. But the easiest way to find a map from a curve to a smaller genus curve is to compute its automorphism group and take quotients. Jeremy and I were surprised to find that Magma is very fast at computing automorphism groups of curves over finite fields, and very slow at computing automorphism groups of curves over number fields and sometimes over Q. And we were more surprised when the following ridiculous procedure seemed to work faster than what Magma does. So the automorphism group scheme of C is finite, and if it's canonically embedded, you can write out equations for the automorphism group scheme, just in terms of matrices and relations. And you can find mod p points on this using Magma's quick black box procedure for finding automorphism groups. And then you can try to Hensel lift this point to a ZP point. Now, of course, curves can have more automorphisms mod p than globally, but in which case you'll just get stuck when you try to Hensel lift it. But then these automorphism group schemes are finite. So if you do successfully Hensel lift the equations of this automorphism, well, that ZP point is actually going to come from a K point for some number field extension. And this is actually a lot faster than just typing automorphism group into Magma. Code for all of this is available on Jeremy's webpage, as well as an interactive webpage for just kind of messing around with the different subgroups and interesting properties of them and equations. Also, this is all in the LMFDB now. That's it. Thank you.
Okay, for questions, we're going to either try to use the microphone or else force him to repeat the question. So, all right, are there any questions?
Okay, so a few slides from the end, you had wait, go forward. Yeah, where you divide your curve into 4 categories. I see why you're more optimistic about the one that satisfies the Chabot condition, but can you just say, as somebody who doesn't have a feel for actually doing these computations, like, how do you get to these 3 different feeling tones about these 3 classes of curves? Like, what makes you more or less optimistic about your ability to control the points if they're all past the Chabot range?
Well, to be fair, I made this slide a year ago, and To be fair, I made this slide a year ago, and I would say the cautiously optimistic I'm more optimistic about now. It's just that I don't personally know how to do it yet and have to rely on other people.
Well, what's the difference between the groups of curves? That's what I'm trying to
Oh, great. In that third, oh, sorry, what's different about these? Oh yeah, just what's different? Yeah. The genera are small. Even for non-abelian Chabot, that cautiously optimistic case, the genus is 2243. There's already a paper where somebody has executed non-abelian Chabot on a genus 3 curve with rank 3. So I'm optimistic about this other genus 3 curve with rank 3. I'm not optimistic about the genus 511 curve.
I have another question, but I should let other people go first. So I'll take it back.
Okay, are there other questions?
You said something about that you can use Sutherland's method to compute the L functions.
Yeah.
So when is that simpler than trying to use modular forms, like realize the Jacobian is?
Well, for one, it's faster, and also it's easier to do this with proof. So Jeremy hasn't. We've also tried everything we could do with modular forms as well. One thing is for these general, I argue about this constantly with people, including like John Voight recently, but we don't know that these curves are of GL2 type yet. For instance, so we don't know that Cayley-Vaughan's theorem applies to these. It should, and in practice, everything's of GL2 type, but we can't. Actually, I think now we figured out how to apply Cayley-Vaughan's theorem. So we don't actually provably know that these modular form computations would work, but in practice what we do is we write down all the modular forms we know, we compute some traces for these, and we match up what we think the factors of the Jacobian should be in terms of modular forms. I should also say Drew's method is a little faster in that there are a couple cases where he had a high genus curve and he computed that there were no F2 points.
Okay, any more questions? Jordan, did you have something?
Okay.
All right, this is a kind of weird question, but as you said at the beginning, we know that for any elliptic curve, the set of exceptional primes, like primes where the Galois representation is non-surjective, we know that that's some finite set. And people conjecture that maybe that can be done uniformly in E, but we don't know how to do that. Mm-hmm. So in the spirit of this Heath-Brown result that I mentioned, I wonder, are there any uniform bounds in E if I say, okay, the number of primes up to X, which are exceptional, do you think there are bounds that don't depend on E as a function of X?
Meaning where you have a maybe.
I mean, it's sort of
a question. I'm not sure. That's a great question.
Okay.
Okay, any more questions? All right, so we'll have a coffee break then until 4 p.m. And thank you.